We're learning how to use energy to solve certain types of motion problems because energy is a nice, simple way compared to forces if you're able to use it. And we've said that if there is no outside force doing work on an object as it moves around, then its mechanical energy stays the same. That the mechanical energy at the beginning of the problem and at the end of the problem will be the same. And that's proved very useful in solving all kinds of motion problems. However, it's not always going to be true. For example, I have this object here, this book, and if I do some work and give it some kinetic energy and let it go, it comes to a stop. Now, the mechanical energy at the end is definitely not the same as at the beginning. It lost some along the way. Now, why is that? Well, because there was an outside force doing work on the book as it slid, which was friction. Friction was pulling back against the book, and it did negative work and took away some of the energy. Now, energy is never truly lost. So if it lost its mechanical energy, it must have gone somewhere. Where did the energy go? Well, it turns out when it slid across the table, that energy turned into heat, which is another form of energy we're going to talk about later in the course. That the kinetic energy the book had at the start, as it slid, turned into heat, and if you could measure the temperature or feel the temperature of the table afterwards, it would be slightly higher, and all the energy was taken away from the book. So the point is that mechanical energy is not always conserved. If there is some outside force doing work, it can give more energy to the object if it does positive work, or it can take away energy like friction. So the point here, as I said, if there's an outside force other than gravity that's pulling on the book, trying to speed it up or slow it down, it's doing work. If it does positive work, it will give more energy to the object. If it does negative work, pulling against the motion, then it takes that energy away. And so in a more realistic type of problem, there will be some outside forces, but it's really not that much harder to include. So to get the picture straight in your head here, imagine we've got this object, and it starts with some mechanical energy, MEI. It's moving along at some speed. And just to put numbers on it, let's say that it's got 10 joules of mechanical energy. Now, instead of just letting it roll, we're going to apply a force to this over some distance, d. And you know, when you apply a force over a distance, you do work. So we're going to do some work here. And just to put numbers on it, let's say it worked out to be 20 joules of work that you put into the motion. At the end, the car, because you're pushing it, is going to be going a little faster, right? VF. And it's going to have some mechanical energy at the end. Now, let's think. It's not really that hard here. If you started with 10 joules and you did 20 joules of work, giving 20 joules of energy to the object, guess how much it ends up with? Well, it started with 10, you added 20, surprise, surprise, it ended up with 30 joules at the end. So the energy at the end is what you started with plus what you added to it. Okay, so mechanical energy at the end of the problem is however much it had at the start plus the energy that was added by work. And if it's a positive work, then it has more energy. And if it's negative work, then you're adding a negative and it has less. So in other words, the mechanical energy at the end is the mechanical energy at the start plus any additional work that's added along the way. So it's just like what we've been doing, except we're going to add some additional work from an outside force. So here's how the math is going to work out. Said if there's an outside force other than gravity, we've already built gravity in to the potential energy, that's pulling on the object, speeding it up, slowing it down, giving it energy. Okay? The energy at the end is what you start with plus what you added. Now recall, mechanical energy means kinetic plus potential. So if you throw in the equations for all of that stuff, you get this gigantically long equation at the bottom. And what this says is that the kinetic and potential at the end is what you started with, plus anything extra added by work. Now this is really long and ugly. I remember this one up here with the mechanical energies and just put in whatever energy is necessary. But this will be in your notebook, and you can look this up, and you can start with this equation. It's big and long and ugly, but it's okay. They're going to tell you some of the stuff, and then you have to calculate whatever it is that's missing. So let's try this out, and it takes a while to get used to that, so we're going to do plenty of examples of using this energy with work. So we'll start with a car moving on some flat ground at a certain speed there. Its engine creates a force over a distance, and I want to know what its final velocity is. Now we could have solved this in the previous chapter about forces. The force would make an acceleration and use the old motion equations. But we're going to do it with energy because it's easier. Maybe not in one dimension, which is what this is, but in 2 dimensions it's a lot easier. So I want to learn how to do it in 1, and then we can extend it out to 2. So we got the car, got a mass, moving at some starting velocity, v initial. There's a force over the distance that does work. So it's pretty much the same picture I had before, just with a different looking car. So it does some work here that adds energy to the object. So at the end, it's got more. Now I kept the ground flat, so we don't need to worry about potential energy. The height of everything is 0. And what we're looking for is how fast is it going at the end. So instead of using forces and accelerations, well, you're going to use energy. All right? The energy at the end of the problem is what it started with, plus anything added by work. The big old long version, 1/2 mvi squared, that's the final, plus mghf, that's the final kinetic and potential, is what you started with, so you put i's on it, plus the work, f d cosine theta. Yikes, it barely fits on the board. But we're going to cancel out some of these guys because there's some zeros. It starts at a height of 0, because it's on flat ground, and it ends at a height of 0. So the potential energy terms go away. We're only talking kinetic here. Now, in the previous section where we didn't have work, we would then go on and cancel the m's. But remember, to cancel a variable, every single term has to have one. This has an m. This one has an m. Does this one have an m? No, unfortunately it doesn't. So we can't cancel the m's now that there's work. But that's okay. We know what it is. We don't need to cancel it. So what we're trying to find is VF. We need to move the half and the m over to the other side. So we'll start by multiplying both sides by 2 to get rid of the 1/2. It's getting pretty long. Let me write this again. We'll multiply both sides by 2 and cancel out the stuff, and we'll get mv final squared is, we take 2 times that, mv initial squared plus 2, both things need to be multiplied by 2, 2fd cosine theta. All right, let's figure out what theta. Theta is the angle between f and d. They point in the same direction, so the angle between them is 0. And the cosine of 0 is 1. Basically, the cosine term just goes away. And we're about done. If you want VF, you just divide both sides by m, and that's VF squared, so you take the square root. Divide both sides by m, take the square root, and there you have a big, long, ugly equation, yes, but look, it took 1, 2, 3 lines of algebra to get there. It's not too bad. So the velocity is, there's lots of things to put in this time. The mass, it's 955 times VI squared, 7.25 squared, plus 2 times the force, 1250, times d, that's the distance, 32.8, times cosine of 0, which is 1, then that whole mess over the mass, which was 955. Woo! Okay, entering this in your calculator, be careful. Put a big parenthesis around the top, or hit enter when you're entering it in your calculator. So, the velocity is square root, parentheses, another parentheses at the top, 955 times 7.25 squared, plus 2 times 1250 times 32.8. Close the top parenthesis, divided by 955, close the outer parenthesis, 11.8 meters per second. And there, we solved for velocity without using forces, without using accelerations, using only the energies. Now, in one dimension, like this, we could have solved that fairly easily the old way. This may not actually be much of an improvement, but the same math works for a two-dimensional force, and then saves us all that sort of vector math. So as a more two-dimensional example, we'll go back to this problem where a woman is pulling a suitcase, presumably in an airport. We have a force, we have a distance, there's friction pulling back. And the things are not all along a straight line, so it's a 2D force problem. Now you remember in the old section, to do a 2D force problem, you'd break all the components in X and Y and solve X and solve Y and put it back together again. You don't need to, because energy is not a vector. So, suitcase, I don't know if it's got rolly wheels or not. We've got this force at a 52-degree angle. We'll call it F1. D, I assume the airport is flat, so it's horizontal. And we've got friction pulling back directly against the motion at 12.7. Now I want to know the total work done, and once we find that, we can figure out the speed of the suitcase. Well, these are not the only forces. There's also the normal force and the weight, but both of those are perpendicular to D, and if you remember, a force that's perpendicular doesn't do any work. They're not making it speed up or slow down. This force is trying to speed it up. He's doing plus work. This force is trying to slow it down. He's doing negative work. So we got to find those two and add them together to see how much work was done on this suitcase. All right, well, let's find the work that force 1 did. That's F1D cosine of its angle, which was 52.7. Okay, so I'm just going to put that in the calculator. F1 was 27.2 times the distance, which is not stated in this problem. So whoever wrote this problem really needed to put a distance in. So since it was me, I'm going to add a distance. Let's just say that she pulled it by 20 meters. Sorry about that. Okay, that is necessary. So now that we've got D, we've got F times the distance times cosine of the angle. And so this force did 330 joules of work, and that 0 is significant. Okay, the force pulling back is friction. You may recall friction does negative work. It takes energy away. And that's the force of friction times D times cosine of its angle. Now, its angle is not 52.7. The angle between D and F for the friction is 180 degrees. That's always the case for friction. It's always the exact opposite of the way you're moving. And cosine of 180 is -1. So the work that friction did is 12.7. That's the force. The distance, now known to be 20. Cosine of 180, which gives you a minus sign, So 12.7 times 20 times -1, -254. Okay, the lady put in 330 joules of work. Friction took away 254 of it. So the total work is the sum of those two things. That's equal to, she did 330. Friction took away 254. So overall, the suitcase gained 76 joules. And I lost a sig fig in the process. So we only have 2 now. Okay, it's got 76 more joules of energy than it started with. So it started with none. It gained 76. So at the end, it's got 76. And what kind of energy? Is it going uphill? No. So it doesn't have any potential. This means at the end, it's got 76 joules of kinetic energy. To show the work, the mechanical energy at the end is the mechanical energy at the start plus the work. At the start, it was on the ground, so no potential. It was not moving, so no kinetic. So there was no mechanical energy to start with. It was all 0. At the end of the problem, it's still at 0 height, but it is moving, so the final energy is all kinetic. 1/2 mv squared, and that equals 276. So if you want to find the velocity, you multiply by 2, you divide by m, then that's v squared, you take the square root. Vf is square root of 2 times 76 over the mass. The mass was 9.87. Okay, so at the end of the problem, the suitcase is going to 2 sig figs, 3.9 meters per second. All right, well, there's still quite a few steps here, but it is better than taking all the vector components and doing them separately. So with work, when you have that as part of your energy, you just have to add it on to the mechanical energy. The energy at the end of the problem will be what you started with, plus however much got added by work. And from there, you can find anything about the motion of the object.